Hi guys, welcome to another part of lecture 2. And in this part, we are gonna look the Bayes rule. Okay, the Bayes rule is a really powerful theorem you can use in many different problems. So first look at the formal definition. And let's say we have some events from A1 to AN, and they are the disjoint events. And also they form a partition of a sample space with the probability of greater than 0. Okay. Then for any event B such that the probability of B is greater than 0, we can calculate the probability of AI. It can be A1, A2, A3, AN, given B. And we can use this formulation, P probability of AI times probability of B given AI divided by probability of B. And we can extend this by extend this part, okay, like that one. So we can use this probability when we are asked to when we are given B and ask for the AI, right? Okay, remember the chess game example. In this example, if we are given that we win the game, what's the probability of our opponents is from type 1, type 2, and type 3. Okay, so we look the problem from different way. Okay, just to understand the logic of the Bayes theorem, let's draw some. Okay, so let me clear this thing first. Okay. I'm sorry, that is. Okay, so let me create a new board. So the first thing, what we are calculating. In this case, we are calculating the probability of AI given B, right? And we said that we can calculate this with this formulation, probability of AI times probability of B given AI divided by probability of B, right? So let's write it. The probability of AI times probability of B given AI and divided by probability of B. Okay, let's draw something and try to understand the logic behind the Bayes theorem. Let's say we have a sample space. Okay. And okay, let's do this with the two events, A1 and A2. Okay. Let's say this is A1 and this is an A2. So the partition of them are the sample space. And let's say we have another event, which is the B, right? Which is B. So in this case, what we are asked for, the B will be given. So we know that, let me change the color. We know that the points or the samples from this region, right? Okay. And what we are asking is AI, right? And let's say we are asking A1. So simply I will calculate, let me change the color. I will calculate the probability of A1 given B, right? So in this case, I will look for this part, right? Because this part belongs to AI, A1, and also B, and this is given to me this piece of information. So simply I can say that I can calculate the probability simply. I can divide this part, the small part, to entire B, right? Okay, so what is here? This is simply the A1 intersect with B, right? Okay, keep this information in your mind. And what's the whole region? It's the B, right? So simply, this is actually what I'm asked, right? So let's write this one uh, in another way by using the definition of the conditional probability. So let's write here the definition of the conditional probability. If B given A, which is the probability of B intersect A divided by P A. Also, if I write the A given B, it is the probability of um, B intersect A. Actually, it's the same. B intersect A or A intersect B is the same. So divide by P. So keep this formulations, and we are going to use that one. So, okay, let's write this one. Okay, so I can use this part, right? And I can rewrite A intersect with B such that this is actually the probability of um, multiplication of this two term, right? So PA, in this case PA1, times probability of E given A. And now let's write the B, right? So how can I write the B? And actually B is equal to probability of B intersect A1, this part, and plus the probability of B intersect A2, right? So as I did here, I can extend this two parts separately, right? So instead of this one, I can write PA1 times P given A, and this is coming from the same thing from here. And for this one, this is a one. And the second one is probability of A2 and times this is A1, and the probability of E intersect A2, right? So, and this is actually exactly what the Bayes theorem is. Let's look at here, right? That's the same thing. So we derive this property or this formulation from the definition of the conditional probability. So I hope it's clear, but let's look at the example and we will revisit the aircraft detection problem. I want you to understand it in a better way. I mean, I will try to explain this problem by visually, or you can only use the formulation if you are okay with the concept, okay? So what was the problem? So let A be the event that an aircraft is present, and let B the event that a radar generates an alarm, right? So if you don't remember this problem, revisit previous slides and check it. Also, we defined A complement, which is the event that an aircraft is not present, and B complement is the event that the radar doesn't generate an alarm, right? And also we are given some information like probability of B given A is 0.99. Probability of B given A complement is 0.1. And probability of A is 0.05. So in this example, the new question is, what is the probability that there is an aircraft present given the radar just has just generated an alarm, right? So what we are asked is probability of the given the radar has just generated an alarm. So what is the B, right? So B is given. The radar has generated an alarm, which is given, and I I am asked for the probability of A, right? So am I right? So what is the probability that there is an aircraft present given the radar just has generated an alarm? So this is the question. Okay, so let's let me create. Okay, let's draw it again. So okay, just to make it easier and understand. Let's say I have my omega, and this is A. This is a complement. That means the aircraft present, and A complement is aircraft is not present. And let's say this is the B, right? And what is the B? The radar um, generates an alarm. Okay. So, and what I'm asking for, the probability of A given B, right? The question is probability of A given B. Let's ask. So again, let's write the condition probability definition again. So probability of A given B is the probability of probability of A intersect B and probability of B and probability of B given A is equal to probability of A intersect B divided by P. Okay, so we will use this one. Okay, so let's say let's draw what we are asked. Okay, so the first one, the B is given. So I'm gonna look at this part, right? This part. So I know the sample points will be from this region, and given that part, the probability of A. So in this case, I need to calculate this part, right? So what is this part? This part is simply the A intersect B, right? So simply this one, the probability of, sorry, the probability of A given B is equal to the probability of A intersect B divided by P, right? Okay, by using the definition of conditional probability, let's uh, let's write this one in another way. But okay, so the first, let me write the given information here. So P, A, these are the given one. A is 0.99, I think. Yes, and BA complement. So BA complement is 0.1, and the last one is, I think, probability of A is 0.05. Probability of A is 0.05. So from this one, I can also, this one, I can say that probability of B complement A complement is 0.9, right? Okay, so let's rewrite this one by using this formulations, and I can rewrite this one as simply multiplication of this two term, right? So one can say that I can also use this definition. It is because it's the same, right? But why I'm using this one? Because it's easier. Why? Because I know the probability of PA and uh, B given A. So I can use the numbers. That's why I'm using this one. If you have these numbers, you can also use these ones. This is the one I am asking actually. So that's not logical, but using this one makes sense. So let's rewrite this one, which is the probability of B given A times probability of A. And let's write the PB. And this PB, the probability of B, is actually the probability of A intersect B, this part, plus, let me change the color, and plus this part, right? So I can say that, which is the probability of B intersect A complement. So this is the denominator of this formulation. So for this one, again, I can use the conditional probability definition, and I can rewrite this one by multiply this two term again. Okay, so it will be probability of B given A times PA times this part is I can rewrite which one is useful for me. Let's say I think I'm giving this information, so I can use this one, like probability of B a complement can be written as probability of B intersect a complement divided by P a complement, right? So I'm giving this one. So I was given this one and this one. So I can rewrite this part as, and this part is equal to this one, probability of B given a complement times P a complement, right? So this is exactly what the Bayes theorem is. You can double check this part. So this is given. This one is 0.99 times PA is given 0.05 divided by same times 0.5 plus this one is also given here 0.1 times PA complement. If I know the A complement will be 1 minus 0.05. This is A and this is A complement. So if I calculate this formulation, I will get almost this one. Okay, approximately it's the 0.3426. Okay, so let me double check. Okay, so this is the formulation and this is the logic behind how I use where the Bayes theorem is coming from. Okay, So let's look at another example. So a test for a certain rare disease is assumed to be correct 95% of the time. And if a person has the disease, and the test results are positive with the probability of 0.5, and if the person doesn't have the disease, the test results are negative with the probability of 0.95. So a random person drawn from a certain population has probability of 0.001 of having the disease. And given that the person just tested positive, and this information is given, that tested positive, what is the probability of having the disease? Okay. So let's A is the event that has a person had let A be the event that the person has the disease, and let B the event that the result is positive. Okay, so let's draw this one again. And let's say this is A, and A is has disease. Let's say this is disease, and this part is a complement, no disease. Okay, and let's say, oops, sorry. Okay, let's say, sorry. Let's say this is event B, and the B is, I think that test positive, right? The result is positive. Positive. So what I'm given, the probability of B given A is 0.95, which is, if I'm giving that the person has disease, the results will be positive. Okay, so let's write it. P B given A is 0.95, I think. Yes. And probability of B complement given A complement. If the result, if a person has not disease, the results will be negative. So which is probability of B complement and A complement is 0.5. And PA is 0.001, I think, right? Yes. So there is a solution here, but I want you to solve this problem as we did in the aircraft example, like this one, okay? So step by step. Okay, so just a hint, we are asked for, what's this? Given that the person just tested positive, what is the probability of having the disease, right? So that we are asked probability of given B, the test result is positive from this region, what is the probability of A have a disease? So we will solve this question, or you will solve this question in home, and one of you try to solve this question on the board in the class, and if not, we will do it together. Okay, so these are the hints and how we start to solve this question as we did in the aircraft example. So you will follow the same path, and you can just draw the region. You can use your logic, that what what corresponds to that drone or that shaded region, and then you can deduce some simple operations, okay, as we did in the aircraft example. So please solve this question uh, at home, and one of you will try to solve this in class. If not, we will do it together, okay? So I will see you in another lecture, and I think we will continue with the independence in the probability models.